Hi everybody, here we are to do your second free response problem. In this problem we have a square loop of wire, 0.15 meters on each side. It has a resistance of 0.5 ohms. The loop is moved at a constant speed in 0.2 seconds from position 1 where the magnetic field is 0 to position 2 where the magnetic field is 0.8 Teslas. And part A says, what is the induced EMF in the loop during this period of time? So our equation for EMF is EMF equals negative N, right, change in flux over time. And the thing that we don't have here is the flux yet. They don't give us the flux in the paragraph right here describing what's going on in the problem. And actually, you know what, I didn't do this on the other problem. Now here I forgot to do it again on this problem. Let's make a list, right? Let's make a list of all the variables that we have here, right? So we have a square loop of wire, right? So it says 0.15 meters on each side. So I'm going to say length equals 0.15 meters and the width equals 0.15 meters. It has a resistance of 0.5 ohms. It's moved in a time of 0.2 seconds, right? From B naught is 0, and let's write this as B final equals 0.8 Teslas. All right, so those are all the variables they give us, right? And so the first thing we need to do from all of this is figure out what the flux is, right? Because we've got the time and it's a square loop, right? So this really tells us N equals 1. All right, so let's figure out our flux, right? Our flux initial, right, is going to be 0, right, because it's outside of the field. Our final flux, right, is going to be B final times area, right, which in this case is length times width, right? So this is B final times length times width, right? I'll put an X there for multiply, right? So this is 0.8 times 0.15 times 0.15. And that tells us that our flux here is 0.018 Webers. Okay, and since the initial flux is 0, right, really this whole thing, right, is our delta flux, right? So 0.018 Webers is our change in flux. Right, so now that we did that hard part, right, now we can do the EMF, right, is negative N, change in flux over time. Right, and in this case, N is 1, right? So we just have 0.018 over, what was the time here? 0.2. So our EMF comes out to be 0.09, and our units are volts. All right, so for part 2, or part B, what is the direction of the induced current in the loop? So we start off with nothing. We end up here with X's. Now remember, the direction of that current is to replace the initial, or go back to the initial magnetic field, right? So if I want to go back to nothing, right, I need to add these dots to cancel out all those X's, right? So we want to add dots, right, or add a magnetic field that's coming out of the page, right? And in order to do that, the current must flow in a counterclockwise direction. Part C says, what is the magnitude of the induced current in the loop? So we know that the current, right, is voltage over resistance. And in this case, we're just going to substitute EMF for the voltage, right? So I can write the current is the EMF over the resistance. And the EMF is 0.09 volts. And the resistance, they told us, was 0.5 ohms. And when I do that, plug that all in the calculator, I get the current is 0.18 amps. All right, part D, right? Power dissipated in the loop. That word dissipated, students don't always like that. You can, right? You don't even have to like read that word, right? So what is the power in the loop? Dissipated just means given off by the loop or used up by the loop. So don't even worry about that. What is the power used by the loop? Right, P equals IV, but in this case we'll write this as P equals the current times the EMF. Okay, so the current is 0.18 amps. The EMF was 0.09 volts. We can multiply those two, and I get my power is 0.0162 watts. Right? Remember, watts is the unit here for power. All right, and last part. How much force is required to move the coil from position 1 to position 2? Okay, so the equation that we can use for this is actually F equals I L B, and this is one from last chapter. Okay, and so the force is going to equal the current, right, which is 0.18, and then L is the length, right? So really, when we look at what L is, it's really the length, right, of the rod, or the length of the piece that's going into the magnetic field. So just use that length. In this case, it's not that difficult because we have a square. But if you had a shape that was a rectangle, right, going into the magnetic field, right, you would only use for your length, you would use this leading edge. Don't use the whole length, and don't use the long side. Use the part that's being pushed into the magnetic field. So in this case, right, it's 0.15, or no, oops, a mistake there, right? Our length is 0.15, and then our magnetic field was 0.8 Teslas. Again, I put that whole thing in my calculator, and what we get out is 0.0216, and since it's force, the units are in newtons. So there you go, there's our last answer. All right, so this problem here is very similar. If you kind of look through and follow the steps, this one is very similar to problems here, number 3. Right, here's a square loop being pushed into the magnetic field. And here's another one, 4. Another loop. This time it's being pushed out of the magnetic field. Really won't change anything. The only thing that'll change is the sign on that change in flux, but that won't matter anyway. So yeah, so you can do problems number 3 and 4 for homework, along with actually problems number 1 and 2, and you should be pretty much set for the free response on your test on, I believe, Wednesday. Okay? Have a good evening.